Hello everyone, welcome to Vision Tech Solutions channel. In this video, I'm going to talk about the spanning tree protocol, its functions in the network. Then we'll talk about the how to elect the root bridge in the network, and finally we'll focus on the rapid spanning tree protocol. So first, let's see what spanning tree is and what is its function in the network. So spanning tree protocol is a mechanism for preventing the loop in the network. And we usually tend to have redundancy in the networks to provide fault tolerance, and this redundancy that we use in the network will cause some issues, like cause the packets to be passed between the redundant paths endlessly, and it will cause the bridging loop. So to prevent this bridging loops, the IEEE 802.1 committee defined a standard called the spanning tree algorithm, or spanning tree protocol, STP or STA. So how STP works is actually a kind of link management protocol that provides path redundancy while preventing undesirable loops in the network. And for Ethernet network to function, properly, only one active path should exist between two stations. So suppose we have two stations connected to two switches, switch A and switch B, and there are two links. Instead of having one link, we have one other link as a redundancy. So in case one link goes down, the other link we have backup. But this way we will have a loop, and let's see how loop happens in the network. So first, if PCA wants to talk to PCB, it sends a broadcast message to switch A, and the switch A will receive this packet and it will forward it to all the other ports except the port that received the broadcast on. So it received it on fast Ethernet 05, so it will send it to 00 and 01. So switch B, suppose the first time that the packet comes in from fast Ethernet 00, so it will forward the packet to its all other ports 05 and 01. And the next time when the packet comes from 01, again it sends it to 00 and 05, and this will continue, and it will bring the network down and will create a loop in the network. So that is something called, we call it broadcast store. And then of course we will have some other problems like multiple frame transmission or MAC address table instability. These are the issues that will happen in the network. So in order to prevent this, the spanning tree will block one of the ports, so the packets will not loop around the network. And that is the mechanism that the spanning tree actually does in order to prevent loops in the network. And how it works, actually there are three phases. The first phase is to elect the root bridge, which I will talk later how we elect the root bridge in the network. And then we will select one root port per non-root bridge, and selecting one designated port on each network segment. So if you look at this diagram, so you will see that PCA and PCB, so the first time they claim themselves to be the root bridge by sending the BPDUs, or bridge protocol data units. These messages that are exchanged between these two switches contain the bridge IDs of the root bridge and the bridge ID of the transmitting bridge. So in the initial stage, because they both claim themselves to be the root bridge, the bridge ID of the root bridge and the bridge ID of the transmitting bridge are the same. And the bridge ID actually is composed of bridge priority, which is from 0 to 65535, 2 byte, and the bridge MAC address 6 byte. So bridge ID is bridge priority plus MAC address. For example, the bridge priority of switch A is 32768, and the MAC address is this number 00000000.9999, and the bridge ID is this number. For the bridge, for the switch B, because the MAC address is different, so it has a different bridge ID. So it will compare the bridge IDs after they received each other's BPDU. The lowest bridge ID wins the election, and it will be elected as the root. So switch B here has the lowest, has a lower MAC address, so it will become the root bridge. So after the root bridge is elected, what happens? It's in the second phase is to select one root per non-root, one root port per the root bridge. So this is two, as you can see, two MAC addresses of switch A, switch B, and here is I'm the root, and here is my BPDU because it has a lower. So then when the switch B is selected as a root port, as a root bridge, it will put all its interfaces into forwarding state. They are called designated. So all its ports are in forwarding state. And then in the second phase, which is selecting one root port per root bridge, root port actually is the port that is closest to the root bridge. Actually, when we say the closest is the port that is receiving the lowest cost BPDU from the root. So the cost of the ports is based on the link speed. As you can see, if the link is 10 megabit per second, the cost is 100. For when the speed or the bandwidth of the link is higher, the cost is lower because it can transmit frames faster, of course. 100 megabit per second, cost is 19. From the 1 gigabit per second, previous IEEE specification was 10, but now it's 19. So 1 gigabit per second 4, and 10 is 10 gigabit per second is 2. So based on that, if you look at switch A, we have two links. One link is 100 megabit per second, and one is 10 megabit. Of course, 100 megabit per second has a lower cost, 19. So the port that has the lowest cost BPDU from the root, which is switch B, will be elected as a root port. So this one will become the root, and the other port will be blocked. And then the network will be actually converged. So that is how it will work. And so it is the designated. These are the designated ports on switch B, which is the root bridge. All the ports are designated forwarding. This one has the lowest cost to the root bridge, which is called the root port, and the other port, which is non-designated, and it will be blocked. So there are actually in several port states when this actually blocking of ports or selecting the root port will happen. There are different states. So when the STP is enabled, every switch in the network goes through the blocking state, and eventually it will go to the listening and learning, and then it is either blocking or forwarding. So blocking means no user data is sent or received in the link, but it may go into forwarding mode. So still BPDU data is still received in blocking state, but discards frame and doesn't learn the MAC addresses. In the listening, the switch processes actually BPDUs and awaits possible new information that would cause it to return to the blocking state, discards frames and MAC address. In the learning, receives and transmits BPDU and learns MAC addresses, but doesn't yet forward the frames, and in the forwarding, receives and sends data. Normal operation learns MAC addresses and receives the transmits BPDU. So as you can see, blocking, listening, learning, and forwarding. Only when it goes to the forwarding state will forward data. And there is something called max age. So how long any bridge should wait after bridging, after beginning to not hear hellos. When it doesn't receive hello or BPDUs, and it will actually trigger the topology change notification, or TNC. We call it topology change notification. Will change the STP topology, and the default is 20 seconds. And the forward delay is also important, is the delay that affects the time involved when an interface changes from blocking to forwarding. So it is 15 seconds. A port stays in listening state and then learning state, and it is defined by the actually forwarding delay, and I will discuss it later. The spanning tree algorithms provides the following benefits: eliminates bridging loops, provides redundant paths, and enables dynamic row configuration, recovers automatically from a topology change or device failure, and identifies the optimal path between any two packet devices. Okay, so now suppose the root port is cut, or this port goes down, the port which is going to the root port. And what happens in this case? Switch A will wait for the max H seconds before it begins to transition fast 0 from blocking. Then it goes to the listening, and in the listening state it must wait for the forward delay seconds actually to move to the learning state, and then it will continue to wait for more forward delay seconds, and if no BPDU is received, it is then placed in forwarding state. So after that, this non-designated or blocking port will be put into forwarding state. So let's look at another topology. So here we have a root bridge, which is put into all the port is designated ports is forwarding. So switch B, the port which is going with the lowest cost to the root bridge is this link. It is a directly connected link. It is it has put into the root port, and the other one is a designated port. And as you can see, this port in switch C, actually again the closest link, the closest cost is this directly connected link, which is going to, that is called the root port, and the other port which has the higher cost is put into non-designated and blocking port. And again, if this link goes down, the other one will be put into the forwarding state. This is another example of when the of course it has to go from the blocking, listening, learning, and the forwarding delay. And STP actually is not very fast. That's why we use the Rapid Spanning Tree protocol. Now I'm gonna talk about how we elect the how is the process of root port election. So STP root port election. So suppose we have these four switches with these priority and MAC address, and as you know, the bridge ID is a combination of bridge priority plus the MAC address. So for the process of electing the root bridge, there are three phases. The lowest accumulated cost on interfaces toward the root bridge, the lowest sender bridge ID, or the lowest sender port ID. So there are three conditions actually, and as you know, the root port is the port that is closest to the root bridge, which means it is the port that receiving the lowest cost BPDU from the root. So, and every non-root bridge must have a root port, and all ports are placed into forwarding state. So here in this topology, this one has the lowest MAC address among all the other switches. As you can see, MAC address and all have the same priority. So this one is elected as the root bridge. Now, from switch 2 and switch 3 perspective, the lowest cost path or BPDU is the directly connected links to switch 1. So they are put into, so it is cost 4 and it is cost 4. So they are put into the root port. Now from switch 4's perspective, to get to the switch 1, which is the root bridge, we have two paths. One is from switch 3, then switch 1, and one from switch 2 to switch 1. And if you look from switch 4 to switch 1, the cost is 4 plus 4 is 8, but from switch 2 to switch 1 is 19 and 4, because it depends on it is based on the bandwidths of the link. Here we have 1 gigabit, here we have 100 megabit, and here we have again 1 gigabit, which is the cost of 4. And therefore this port will be elected as the root port. So as I said, for electing the root port is the port that has the lowest accumulated costs on interfaces toward the root bridge, or it has the lowest sender bridge ID, or it has the lowest sender port ID. But here in this example, it has the lowest accumulated cost on interfaces toward the root port. That's why it will be put into the root port. So here, if I want to show you another example here, from switch 5 we have two interfaces. So which one will be put into the root port and which one will be put into the because both these ports have the same cost to reach switch 1, which is the root bridge. So here in this example, as I said, the second criteria was the port that it has the lower sender bridge ID or the port ID, because here is fast, it has the lowest fast Ethernet 01, it has the lowest port ID than fast Ethernet 02. So this port will be put if we suppose that they have the same bandwidth, because the same switch, they have the same bandwidth. But this one, because it has the lowest sender port ID. The port ID is 01, which is lower than 02, so that this one will be put into the root port. Now I want to talk about the rapid spanning tree protocol. Because of the issues that we have with the legacy spanning tree, the forwarding delay is too much, so it is not very efficient. That's why it is one of the disadvantages of STP is the low convergence time. Is a very low convergence, which is very important in switch networks. And actually, to overcome this problem, the IEEE came up with the 802.1W, and it is a kind of evolution of the spanning tree protocol. It's called Rapid or RSTP, which is significantly actually reduces the convergence time after a topology change or topology change notification, TCN, is triggered in the network. Like the STP usually takes 30 to 50 seconds to transit from a blocking to forwarding state, but for rapid spanning tree is less than 10 seconds. And so we have different port roles, as you can see here. We have a forwarding, that is root port. We have designated port, alternate port, backup port, and disabled port. Designated port, so the port roles are different from the legacy spanning tree protocol. The designated is a forwarding port for every LAN segment. Alternate port is the best alternate path to the root bridge. This path is different than using the root port. The alternate port moves to the forwarding state if there is a failure on the designated port for the segment. And the backup or redundant path to the segment where another bridge port already connects. The backup port applies only when a single switch has two links to the same segment or the collision domain. To have two links to the same collision domain, the switch must be attached to a hub. And disabled port, not strictly part of STP. A network administrator can manually disable a port in so if we suppose that all the switches have the same priority, and if you look at the MAC address, you can see that this one, the switch 1, has the lowest MAC address, so it will have the lowest bridge ID, and it will be elected as the root bridge, and all its ports will go to the designated port and forwarding. The ports fast Ethernet 0 on switch 2 and 3 are closest to the root bridge in terms of actually according to their path cost. So they will become the root ports, and on the segment between switch 2 and 3, because switch 2 has a lower MAC address than switch 3, so it will advertise a better BPDU on the segment, on this segment. So it has a better BPDU, so it will be designated port. And fast Ethernet 01 on switch 3 will be alternate port. So now for these two ports on this switch, one will become the designated port and the other one will become the backup port. So in case the designated port, because switch 2 actually selects its designated and backup, the decision process involves the following parameters inside the BPDU: the lowest path cost to the root, the lowest sender bridge ID, and the lowest port ID. So the lowest port ID uh, will be elected as the backup port, and the other port will be the designated port. That is how it elects the the backup port and the designated port, which we didn't have these port roles in the legacy STP, and it has a very better actually convergence time, and it is more efficient than the legacy STP. So in the next video, we will have a practical STP lab. I hope this video has been informative, and please don't forget to like and subscribe this video, and see you in the next video. Thank you.